My name is Jack Montoya, and this is Physics 2212 Lab 4, Circuits. The purpose of this lab is to examine the behavior of circuits with resistors both in series and parallel, and examine how resistors and capacitors behave within these circuits, as well as exemplify the loop rule and charge conservation. The results of this lab was we found that physics principles were proved as the measured values were similar to the predicted values for multiple potentials and currents. We found that greater resistance within the circuit led to greater capacitor charging/discharging time. And finally, for the last circuit, we found the RC value to be 5.99 seconds experimentally. Some important concepts for this lab are the loop rule, which states that the potential around a loop will have a net of 0, so all of the changes in potential throughout a loop will cancel each other out. Additionally, the junction rule, which defines conservation of charge, where the currents going into a node will be equal to the currents leaving the node. And finally, we will define a steady-state circuit, which is a circuit where the current at each point is constant and is not changing. For the first circuit that we made, as shown on the right, we were focusing on charge conservation. So we found that the current on both sides of a resistor ended up being the same. Also noted that if we flipped the ammeter to read the current, where it read in the opposite direction of the conventional current, the magnitude was the same, but the sign was negative. Additionally, we found the potential differences across different portions of the circuit, and we noted through the loop rule, and this was proved, that the net change in potential ended up being 0 when we added up all of the separate components. We then created an RC circuit, which contained a resistor in the form of a light bulb, a battery, and to charge a capacitor, and then a capacitor. And to charge the capacitor without a resistor took a lot less time than charging with a resistor in series. And we noted that this was the same for discharging the capacitor as well. The third circuit we used in this lab was a fully charged capacitor, and we measured the voltage across the circuit as the capacitor was discharged. So we took a video of the voltmeter as the capacitor was discharging, and here are a few pictures of the different readings. We used these readings to plot the chart as you see on the top right, and this we found will give us a slope that is equal to the negative inverse of the RC value. So using our slope of negative 0.167, we found that the RC value was 5.99 seconds for this capacitor. So for our discussion, we will discuss how a virtual circuit would compare to the real circuit components that we created, and we found that the real ammeter experiences slight internal resistance compared to an ideal virtual one, and therefore there's a small decrease in electric potential across the real ammeter. Now, if we are completing the lab with real circuit components, the ammeter, how long does it take to charge the capacitor when connected directly to the battery? This time is different. Similarly to the first what if, is that the real capacitor will take longer due to the internal resistance of the wires, and a real ammeter will also add resistance to the circuit and increase the charging time. Thank you for listening.